You are welcome in our organic class. So we start with chapter number 2 about polynuclear aromatic hydrocarbons. Polynuclear aromatic hydrocarbons, also as known as polycyclic aromatic hydrocarbons, of course organic compounds that contain at least from two aromatic rings, two or more, at least two aromatic rings. So can be divided into main family here, the benzenoid, and the second family, the non-benzenoid. From the name, the benzenoid that consists of the benzene cycle, and the non-benzenoid contain another size of the aromatic rings, not the benzene. Also can be fixed rings or bonded by single bond. So the related subject here in this chapter, it will be with the benzenoid compounds. So the benzenoid compounds also divided in the two main groups, the isolated benzenoid compounds, from the name the two cycle or three or more than three cycles separated by single or more than one single bonds. That meaning maybe here we have just a single bond without carbon atoms, or maybe it will be between the two rings there are more than one carbon atoms. The second group, the fused ring. From the name fused, meaning both cycle, they are bonded together directly, and there are at least two carbons atom between the two cycles or the three cycles. The different from the isolated and the fused ring, you are clear here. As I said before, that isolated, they are directly non-bonded together, okay, not bonded together. But for the fused, they are directly bonded together, and there are related carbon atoms between the rings. So we start with the benzenoid compounds. The term benzenoids refer to the class of chemical compounds, especially polycyclic aromatic hydrocarbons, that are structurally composed of the benzene rings, consist of the benzene rings. And the benzenoid can be divided into two main parts, as we said before, that the isolated and the fused benzenoid compound. So we start with the isolated rings benzene, right? As we referred before, that the isolated ring benzenoid generally refer to compound where two or more benzene rings are connected but don't share the common sides, the bonds. Okay, that meaning there are at least single bond between the rings. So rings are connected by single bond or carbon chain, more than maybe just carbon atom or more than one carbon atom, and each ring behaves almost like separated benzene molecules, just alone can be behaved like that, such as biphenyl, two rings join by a line meaning here the bond. So biphenyl compound, the diphenyl compounds, specific class of organic molecules consisting of two benzene rings connected by single bond. Okay, where is here the structure? If we go to the structure here like that, this is the structure here. So we start with how these compounds can be prepared. So the first method to prepare this compound, the biphenyl compounds, is the phytic reaction. The phytic reaction is a classic organic chemicals reactions used to synthesize the biphenyl compounds. and other biaryl compounds, not just uh, biphenyl compounds. So uh, here it is like reaction famous called Wurtz reaction. Instead of joining alkyl chain like Wurtz reaction, it joins two benzene rings together using metallic sodium. So if we go to the Wurtz reaction, what's meaning Wurtz reaction here? Wurtz reaction here, two alkyl halide can be joined, can be coupled to each other, can be joined to each other. We say coupling reaction with sodium metal hydrocarbons by coupling of alkyl halides. So we start with alkyl halide and metals, and the two alkyl halides will be joined to each other to give us RR here. That meaning this the hydrocarbon compounds. The reaction involves taking two molecules of aryl halide here, benzene ring with a halogen. We know what meaning aryl halide. Aryl halide, that meaning the halogen here directly bonded to the sp2 aromatic carbon. So like طبعا here the halogen that used here it will be chlorine or bromine, and treating them with sodium metal in the presence of a dry ether. Okay, the dry ether here must be dry because if we have a small amount of water can be react with the sodiums and the reaction to be not doing well here. Okay, so the reaction is so easy here. We start with two alkyl halide and the aryl part here, this is the aryl part, it will be joined to each other to give us aryl. So another example here is the diol here, the bromobenzene, two bromobenzene, it will be react with each other with the sodium metals in the dry ether to give us the biphenyl compound, and here by skeletal structure also it will be give us idea about how the diol aryl compound can be also go to the coupling here with just aryl with the alkyl to give us coupling reaction, but here the aryl with the alkyl halogen. So we have here a new carbon-carbon bond. Also we have here a new carbon-carbon bond. This is easy example for the coupling reaction. This about phytic reaction. All this is about phytic reactions. Easy, simple reaction. Very useful to synthesis this type of compound. The second reactions is to prepare this type of compound is the Convert-Begemann reaction. It is possible to synthesize biphenyl compounds directly from the benzene diazonium salts. Here we used the diazonium salts to synthesize this type of compound. The specific transformation is known as the Convert-Begemann reactions. If you look here to this reaction, this is the diazonium salt here, and we take it before that how we can prepare the diazonium salts. It will be directly go to the coupling with the benzene ring to give us phenyl carbon-carbon, a new bond here with a second phenyl cycle. In this case, we get the biphenyl compound. So if you look here, another examples, this is the diazonium salts with another aromatic compound here, derived from the aniline. We know the NH2 directly bonded to the benzene cycle. Here it's called aniline. So this is the derivative of the aniline. So it will be has coupling between the diazonium salts and the aniline compounds to give us the derivatives of the biphenyl compounds. Okay, we have here NH2, R group, and this R group it will be different. And here the examples for this different compound here. So if you look, we have fluor, chlor, like that. Very useful reactions to prepare this type of compound. All this derivative for the biphenyl compound. And he said, unlike the phytic reaction which use sodium metal, this reaction use diazonium salt to generate a highly reactive free radical that attack another benzene ring. Okay. To convert benzene diazonium sulfate into biphenyl, you react with benzene. Okay, it will be react with the benzene. Use as both reactant and solvent. The presence of the base, usually aqueous sodium hydroxide, and or sodium hydroxide on sodium acetate, yani in the presence of the base. In the presence of the base here. The third reactions here to prepare this type of the compound is the from benzene diazonium sulfate. Okay, benzene diazonium sulfate, but with the Cu metal here, with the copper metal. We use the copper metal here. So this another chemical method for synthesizing of the biphenyl from the benzene diazonium salt. This reaction is very similar to the method which just discussed here above, is the Komberg-Bigmanen. But in uses of the copper, here the metal will be different. Okay. The other reactions to prepare this type of compound, the biphenyl compound, is convert the benzidine into biphenyl. Okay, convert the benzidine into the biphenyl. Two-step chemicals synthesis route used to convert the benzidine. Benzidine is the biphenyl compound that contain NH2 in the both group in the position number 4 here. 1, 2, 3, 4. That means this is the position number 4. So this compound called benzidine, and it will be convert NH2 group to the diazonium salt. We said diazotization step here, convert the aniline, the NH2 group to the diazonium salt. The second one, elimination of the diazonium groups to the hydrogen. Okay, it will be converted to the biphenyl compound. The second step here is the reductive deamination. Deamination here, that meaning we cancel the amino group. It will be cancelled, and it will be converted to the hydrogen. And this state we said reductive deamination. Reductive deaminations, as it is discussed here. The second reactions to prepare this type of the compound is the Ullmann diaryl synthesis. Okay, Ullmann diaryl synthesis. Ullmann diaryl synthesis also is a classical organic coupling reaction used to join two aryl halide to form symmetrical biaryl compounds. Okay, if you look to the product here, we started with this compound is the 4-iodotoluene. This compound 4-iodotoluene, two compound of 4-iodotoluene to be coupled into coupling with each other, also by using copper to give us symmetrical biaryl compound. Look here, if we have a symmetrical plane here, this part like this part, And here also another example here is this compound is symmetrical. Okay, if we have make rotation here, rotation for this bond, this NO2 group it will be come to here. In this case, if we have rotation, if we rotate this part and this NO2 convert to the up, it will be a symmetrical compound. Also, this compound can be prepared by famous reaction. For us is called the Grignard reagent, and we know what meaning Grignard reagent. We take it before that. Is a very famous reaction. Uh, Always give us a new carbon-carbon bond. A method synthesized biphenyl using Grignard reagent in the presence of the transition metal catalyst. This this is a type of cross-coupling reaction. Cross-coupling reactions. So that meaning, what meaning cross-coupling reaction? Meaning the starting materials here, they are not similar to each other. So this is bromobenzene, but here it is not bromobenzene. So the phenyl magnesium bromide, this is the phenyl magnesium bromide, is called here Grignard reagent. Okay, it acts as a nucleophile, meaning the carbon attached to the magnesium carried a partial negative charge. Here, this phenyl here has negatively charged, so it will be act as a nucleophile. The bromobenzene here, the aryl halide, provide a second phenyl group to the coupling. Okay, for this coupling. This reaction may be needed for catalyst for the cobalt chloride. This is the catalyst, and because here the transition metals like cobalt, nickels, palladiums are essential here for the reaction, because the Grignard reagents typically don't react directly with aryl halide. Okay, that meaning we need catalyst to make this coupling for the starting material for the reactants here to give us the biphenyl compound. This what we talked about it, the methods for preparation of the biphenyl compound. So we go to the second part for this compound is the reactions of biphenyl. How the biphenyl it will be react, the properties of the biphenyls, how the rings it will be react or behave with each other. So here what we learn inshallah about it, the biphenyl here compound is reactivity as dominated by electrophilic aromatic substitution, like benzene. We talk about the reaction of benzene in the organic chemistry. The benzene ring it will be can be entered to the electrophilic aromatic substitution. So the same thing here. In biphenyl, one ring act as electron donating group and the other act as electron withdrawing group. So this benzene ring it will be donate the electron to this second benzene cycle. طبعا by resonance. Here by resonance, if we convert this pi bond to here, and this it will be converted to here to give us negative charge. Also, the negative charge by resonance can be converted to here. So we have here an increased electron density. So in the first cycle, it will be decreased the electron density. This donating, and this it will be withdrawing. The key to understanding the biphenyl is recognize that each phenyl rings act as an ortho-para directing group. Ortho-para directing group. So the orientation for this group in this benzene cycle, it will be what? It will be ortho and para. It will be ortho and para. So if the electrophile it will become to this position. We say position number 2. This 1, 2, 3, 4, 5, 6. It will be 2, 2, or 4 or 6. 2, 4, 6. The position for the substitution. When one rings react, the existing phenyl groups release the electron density via resonance. Okay, via resonance, activating the position at 2, 4, 6. Okay, look, 2, 4, 6. Where's the 2, 4, 6? This 2, this 4, and this the 6th position. So the electrophilic substitution occur in position number 4, the major one. So anyone is the best for substitution, 4 or 2, 6. طبعا of course the 4. Why? Because here we don't have a steric effect and we have open area here, but here this the benzene fake, it will be make steric effect here for us. So it will be the minor product, it will be substituted in the position number 2 or 6, but the major product, it will be substitution on the position number 4. Okay, don't forget that. This is important note. So look here, what type of reaction we see here on this page. If you look, we have here the nitration reaction. Nitration reaction by using concentrated nitric acid and concentrated sulfuric acid, both of them important reagents for the nitration reaction here. And the NO2 group, it will become in position number 2 or position number 4 or 6. Okay, 2 or 6, both of them, they are the same here to give us 2-nitro-biphenyl, 2-nitro-biphenyl. Or in position number 4, it will be 4-nitro-biphenyl. Also, this compound can be entered to the further nitration to give us 3 type of the product. Look here, we have 4,4-dinitro-biphenyl and 2,4-dinitro-biphenyl and 2,2-dinitro-biphenyl. Anyone is the major product if you look to here. Of course, this it will be the major product here, and this it will be the minor product. If we use percentage, maybe this it will be, for example, 50%, and this it will be, for example, maybe 30%, and this it will be 20%, like that. This is the least percentage here, the lower percentage for the yield here to give us the yield, and this is the higher percentage yield here. So it is so clear for us here. Nitration and halogenation and sulfonation and the free Craft acylation, all this, they are type of the electrophilic aromatic substitution. So this about the reactions of the biphenyl compound. So there are another derivative of the, or another derivative for the biphenyl compounds. Here we talk about the benzidine. We said before that the benzidine is the 4,4-diamino biphenyl compound. Okay, this biphenyl compound, and we have here position number 4 and the position number 4 on the second cycle. Here also they are substituted by amino group. Okay, this amino group and this amino group, and the question here is, so show how could you prepare the benzidine from the benzene. Okay, if we want to prepare the benzidine from the benzene, we start with the halogenation by using the iodine and nitric acid to give us iodine on the benzene ring. Okay, iodobenzene. So this compound, it will be entered to the nitration to give us 4-nitro-iodobenzene, and this can be coupled with each other with the same compound, with the itself, can be coupling with the itself here, 2 molecular for this compound to give us 4,4-dinitro biphenyl compound here, and we reduct it will be reduction of the NO2 group to the NH2 group by ZnHCl to convert the NO2 group to the NH2 group. The nitro group to be converted to the amino group, and this is the finally is the benzidine compound. The benzidine compound. So iodination, nitration, it is more explanation for you here if you want to look it about it. And here we have Ullmann coupling reagent, and finally we have reductions for the nitro group to convert to the NH2 group. The second derivative of this biphenyl compound is the diphenic acid. The diphenic acid we have in the position number 2 on both cycle. We have carboxylic acid group. Carboxylic acid group. This compound called diphenic acid. So again, the diphenic acid we said is biphenyl compound substituted with carboxylic acid at position number 2 on both cycle. The preparation of this compound, we have the first method to prepare this compound from anthranylic acid. This is the anthranylic acid. Okay, this synthesis involves two-step process, diazotylation to convert the amino group to the diazonium salt group, and then reductive coupling. The coupling we say self-coupling. Self-coupling, that meaning this molecule will be intercoupling with itself, with the second molecule, like this compound, the same compound, to give us the diphenic acid. The second method to prepare this compound during Ullmann synthesis to couple the diaryl compound that's substituted with the ester group here, and he said that this method uses classical coupling reaction of aryl halide followed by hydrolysis. So the ester here group, after coupling, it will be hydrolysis to the carboxylic acid to give us diphenic acid. So two-step reaction. Step number 1 is coupling reaction, and step number 2 hydrolysis in acidic medium to give us the diphenic acid. And here the Ullmann coupling, for the explanation for this step here, the starting materials ethyl 2-iodobenzoate. This is the ethyl 2-iodobenzoate. The two molecules of this aryl iodides are heated with copper powder here as catalyst metal. The copper removal the iodine atom, and it will be entered to the coupling with the 2-benzene ring together. This is the 2-benzene ring together, and here we will take the carbon-carbon a new bond. The hydrolysis is famous reaction for us to convert the ester group to the carboxylic acid group. Also, we have third method is the oxidation of the phenanthrene or phenanthraquinone compound oxidation, and here phenanthrene can be oxidized by using peroxided hydrogen and heating to give us the diphenic acid, or the phenanthraquinone. Also, it will be entered to the oxidation by using K2Cr2O7 in acidic medium, and here to also give us the diphenic acid. Also, here we have here the explanations of this reaction, here, the bond between carbons C9 and C-carboxyl phenanthrene has significant double bond characters. It behaves somewhat like alkene. okay, somewhat like alkene here. So again, the left pathway oxidation of phenolphthalein, this is the reactions. Here, this is the double bond. It will be a breakdown. This is the double bond, the carbon-carbon double bond, and this cycle it will be open. This cycle it will be open. So the oxidative mixture cleave the specific bond, opening the central ring. He talked about this cycle, the center cycle, 1, 2, 3 cycle, the center cycle, the intermediate here, the mid, the cycle in mid here. This bond it will be open, and the carbons and the break points are fully oxidized into carboxylic acid group. That meaning this bond here it will be carboxylic acid group, and this bond here it will be compared to the carboxylic acid group. The right pathway oxidation of the phenanthraquinone, this the reaction. This the reaction here. The molecules is already partially oxidized. It is an orthoquinone. The strong oxidizing agent attack the bond containing the two carbonyl carbons. Okay, that means here this carbon and this carbon, this carbonyl group and this carbonyl group. So the oxidation here it will be attack this bond between this carbon and this carbon. Okay. This carbon-carbon bond it will be cleaved, and the carbonyl groups are further oxidized up to the carboxylic acid. So the carboxylic acid is the end point for the oxidation, cannot be further oxidized. Now this here carbon has one oxygen, but here the carbon has two oxygen atom. This is full oxidized for the oxidation for the carbon atom. Okay, the final here group it will be carboxylic acid group. Reactions of diphenic acid here, the reaction of diphenic acid. So diphenic acid can be react with acetic anhydride. So it will be react with acetic anhydride. So here we have diphenic acid. It will be react with the acetic anhydride here. The equation above describe the synthesis of diphenic acid anhydride from the diphenic acid. This is a classical dehydration reaction. Okay, classical dehydration reaction, removal of water from the acyclic anhydride. So it will be cancel H2O molecules from this two group. That meaning we cancel hydrogen with the OH group here from here, and this it will be bond to each other from the oxygen and the carbonyl group to give us the anhydride, cyclic anhydride here, and here give us not for us. We said when diphenic acid is heated with acetic anhydride, an intramolecular reaction occur here. Intramolecular reaction occur. That meaning a reaction it will be happened at the same molecules. Okay, and the same molecules. It will be give us cyclic anhydride here. Cyclic anhydride. Also, the diphenic acid can be converted to the 9-fluorinone here, in the below the structure below. This two-step process convert diphenic acid to the 9-fluorinone. It is a classical method for synthesizing cyclic ketone. Okay, this cyclic anhydride, and also can be converted to the cyclic ketone. This product called 9-fluorinone. Okay, by heating with calcium salt. Look here, this is the calcium salts of the carboxylic acid. So the specific method is often referred to as dry distillation. So the distillation here it will be طبعا enter to the closed system without water. We said the condition of the reaction, it will be dry without any molecules of waters here. So this diphenic acid, it will be react with calcium hydroxide. So as the base remove the proton here, and it will be give us coordinated complex here. It's called calcium diphenate, and this here it will be enter to the cyclization to give us cyclic ketone under طبعا high heating. So the first step here, as we said, explained here, formation of the calcium diphenate. The reactions start with diphenic acid, dicarboxylic acid, and calcium hydroxide. This is the calcium hydroxide. It will be react as a base. We said before that it will be remove a proton. The second step here, the pyrolysis, thermal decomposition here. This step. When calcium salt of the dicarboxylic acid are heated strongly, this molecule will be undergo thermal decomposition. We say pyrolysis in chemistry, and the molecule eliminated a molecule of calcium dicarbonate. This ring closer, it will be form 9-fluorinone. This 9-fluorinone. The resulting molecule is ketone, where two benzene rings are fused to the central 5-member ring. This fused 3 cycle rings, but the center cycle it will be 5-membered ring, not 6-member rings. Also, he said that diphenic acid can be react with concentrated H2SO4 here the concentrated H2SO4, also to produce 9-fluorinone for carboxylic acid. This for carboxylic. That meaning, if you look here for the diphenic acid, we know we have a free rotation between this carbon-carbon single bond, and this cycle can be rotate, and this group it will be converted to here, or the reverse is also right. This group it will be converted to this side, okay, to give us this molecules. And here we have cyclization also, cyclization with this position, طبعا by using concentrated H2SO4 to remove H2O molecules, also to give us 9-fluorinone for carboxylic acid. Here in position number 4 we have carboxylic acid group. Initially the diphenic acid is shown in the conformation where the 2 carboxylic acid group here, the 2 carboxylic acid group are in the same side. Look, are in the same side. The 2 single bond connecting of the bicycle of this the bicycle. We have free rotation here. And we know for every carbon-carbon single bond we have free rotation. So the free rotation can be happened to convert to the second conformation here. This is the first conformation, and this is the second conformation. The reagent used concentrated sulfuric acid with loss of water. The sulfuric acid act as both catalyst and dehydrating agent. So the sulfuric acid will be remove the H2O molecules from the compound. This creates a new 5-member rings containing ketone group fusing to the 2 phenyl rings together. Also, diphenic acid can be entered to the oxidation with the magnesium permanganate, KMnO4, to produce phthalic acid. So one of the cycle, this or this, it will be oxidized, it will be converted to the carboxylic acid group. So all this part, it will be converted to the COOH, to the carboxylic group, to give us phthalic acid. In addition, the diphenic acid here, the diphenic acid can be react with the soda lime to to remove the carboxylic acid group, and this reaction called decarboxylation. Decarboxylation. Here, decarboxylation. That meaning removing the carboxylic acid group. Okay, so here what he say, the chemical reactions known as decarboxylation is the reactions removing carboxylic acid release carbon dioxide, especially is illustrated the conversion of diphenic acid into diphenyl using soda lime as reagent. And the soda lime, if you know, is a mixture of sodium hydroxide NaOH and calcium oxide. Calcium oxide. This both of them mix to each other to give out the soda lime. In the process of soda lime, the carboxylic acid group are first converted to their sodium salt, and then carbon-carbon bonds holding to the acid group is to be a breakdown. So the general reaction for the soda lime reaction is this. For example, we take it with the here sodium carboxylate compound with NaOH, CaO heating. That meaning all this part, it will be converted to what? It will be converted to the hydrogen. It will be converted to the hydrogen. Also, we have another type for the isolated diphenyl compound. Isolated compound is the diphenyl methane. Look, this cycle and this cycle separated by methylene group. Chain of the carbon. Here, this example for one carbon atom, and also can be separated by 2 carbon or 3 or 5 more than that. So also this compound can be prepared by different reactions. So the first reaction to prepare this type of the compound by using Friedel-Crafts alkylation reaction, and this famous reaction in organic chemistry, the alkylation, the alkylation of the benzene compound. We take it before that also. So the benzyl chloride, this is the benzyl chloride, react with the benzene, okay? That meaning this is alkyl halide. Now this compound is alkyl halide, not aryl halide. It is alkyl halide. Why alkyl halide? Because the halogen bonded to the sp3 carbon, not aromatic carbon. For this reason, it will be alkyl halide, not aryl halide. It is aromatic compound, yes, aromatic compound, but it is alkyl halide, not aromatic halide. So the benzyl chloride react with the benzene in the presence of طبعا we need Lewis catalyst. Without catalyst, the reaction cannot be happened. So we need catalyst, and our catalyst here is the AlCl3 aluminum chloride to give us the aluminum chloride. طبعا first it will be react with the benzyl chloride to generate the electrophile, and the electrophile, the benzene ring, it will be react with the electrophile, enter to the electrophilic aromatic substitution to give us diphenyl methane, phenyl. This is the diphenyl methane. So he said the Lewis acid catalyst, it is essentially because we said before that because the benzene ring is slightly stable. Okay, so to generate the electrophile, to generate the strong electrophile, the aluminum chloride here, it will be react with aryl halide to generate the electrophile, and then the electrophile, it will be react with the benzene ring. طبعا the aromatic system, it will be breakdown to give us the carbocation, and the carbocation is stable by resonance. This we talk about the mechanism now, okay? And then elimination to generate the aromatic system again. So this about the electrophile. The reaction below here, this is the reaction here. طبعا classical example for the Friedel-Crafts alkylation. It shows the reaction of 2 molecules of the benzene with 1 molecules of the dichloromethane, here dichloromethane. So the first reaction here, طبعا this is two-step reaction. The first one benzene, it will react with the methylene chloride to generate the benzyl chloride, and then the benzyl chloride will be react with the second benzene ring to generate the biphenyl methane, the biphenyl methane. So the CH2 group here from the dichloromethane replace one hydrogen on the each of the benzene ring, link them together. This as a total reaction. The aluminum chloride is طبعا we said it is very essential catalyst here to pull the chlorine of the carbon, allow the carbon to bond with the benzene ring. Okay, so the second here method to prepare this type of the reaction here is the diphenyl methane from the benzophenone. Okay, now what meaning benzophenone? This is the benzophenone, is ketone compound. Benzophenone, if you look, is the ketone, but by two benzene ring from the both side. So this reaction here, if you look, HI with the heating, we need heating. Also, we need reduction here, reduction in acidic medium or in basic medium. The transformation involve the completed removal of the oxygen atom from the carbonyl group here to reductive this carbonyl group to the CH2 group. So replacing here it with two hydrogen atom to form methylene group. That meaning this oxygen will be replaced by two hydrogen atom. This the oxygen. It will be replaced by two hydrogen. The reagent listed are here three most common method for the achieving the deoxygenation. Okay, so the first one here, reduction with HI and red phosphorus here. The HI act as reducing agent and the red phosphorus react with the formed I2 here, the iodine, to generate the HI. The second one here, it is the Clemmensen reduction. Clemmensen reduction in the acidic medium. And the third one is the Wolff-Kishner reduction in the basic medium. You can use this, or you can use this, or you can use this. All of them is useful to convert the carbonyl group to the what? To the CH2O group. So this is the method to prepare the diphenyl methane. So if we talk about the reaction of the biphenyl methane here, if we go to the nitration, all this group is ortho-para-directed. We said before that, that meaning the substitution, it will be happened at position number 264. So the nitration also it is electrophilic type of the electrophilic aromatic substitution. Use nitroxylic acid and sulfuric acid, and the nitro group, the major product, we have it here, the nitro group in the position number 4. So you will be say the nitro group, it will become to here or to the here, the same. There is no different. Further nitration, that meaning the second NO2 group, it will be substituted in the second cycle. To give us bis for nitrophenyl methane. Okay, so this and this two dinitro group substituted in both of the benzene cycle. Halogenation, you know, there are two types of the halogenation. Halogenation by using Lewis acid, halogenation by using free radical reaction in UV light or heating by free radical mechanism. So if the bromine react with the hydrocarbon by in UV or heating, that meaning is a free radical mechanism, and the substitution, it will be happened on the aliphatic part, not on the aromatic part. Okay, why it is not on the aromatic part? Because there is no Lewis catalyst here. There is no we said electrophilic aromatic substitution reaction happened. It will be happened here. So the Br2 group, the bromine, it will be react with the aliphatic part. Where is the aliphatic part? This is the aliphatic part. Okay. So the substitution, the halogenation, it will be happened here, and one of the hydrogen atom, it will be replaced by the halogen, by the bromine. Okay. So the second reaction here is the oxidation is reverse to the reduction. So reduction, the carbonate will be converted to the CH2 group. Here reverse oxidation, that meaning the aliphatic, the CH2 group, it will be converted to the carbonyl group to prepare the benzophenone again. طبعا by using oxidation agent like K2Cr2O7, H2SO4. This is the oxidation reagent. So he said the oxidation of the diphenylmethane to the benzophenone. This is a classical organic chemistry transformation where the methionine group instead يعني situated between two aromatic rings, it will be converted to the carbonyl group. And the hydrogen, the center carbon are benzylic. This is the benzylic because the agent is two aromatic ring. The CH bond are relatively weak, making them highly susceptible to the oxidation. Okay, so the reagent here, I explained for you the reagent here, the potassium dichromate K2Cr2O7. Also the chromic acid here H2Cr2O4. Also the chromic acid is powerful oxidation agent indicated by the symbol for the oxidation for يعني process oxidation process. So we have related subject for the diphenyl compound is the atrop isomers for this related also with the biphenyl compound. What meaning atrop isomers? That we here inshallah talk it about it. So in organic chemistry, atrop isomers are يعني subset stereoisomers. They occur when molecule become chiral, okay, not because a specific center. What meaning specific center here? If you remember when we take the stereo chemistry, we talk about carbon has four different group, so it will be give us isomers for the molecules. So here the stereoisomers, it will be happened not for this type of the molecules that has carbon with four different groups. Okay, stereogenic center, we say stereogenic center atom. Stereogenic center atom, that carbon atoms has four different groups. But here it will be happened because we have restricted rotation between the carbon-carbon bond here, the carbon-carbon bond. Okay, the carbon-carbon bond, there is no free rotation for this carbon-carbon single. So normally he said a single bond between two rings allow them to spin freely without this group, just benzene cycle with the benzene cycle, we have a free rotation here. Here we have a free rotation. But if this position here, this position number 2, 2, 2, 2, this 4 carbon, this 1, 2, 3, if they are substituted with bulky groups, so here this group, it will be physically pumped into each other. That meaning we have a strict handled here, and this group and this group, it will be push each other to give more stable conformation. That meaning this, it will be to the up, and this, it will be to the down, and it will be here this cycle, it will be rotate to be converse to this cycle. So if you use please your imagination, that meaning this, it will be on the plane, this it will be cycle, and this group and this group, it will be on the plane, but here this it will be nearer from you, and this it will be far from you. That meaning this it will be perpendicular, okay, perpendicular to the plane, perpendicular to the plane. So this molecules don't has a plane of symmetry. There is no plane of symmetry. For if we write the mirror image for this molecule, this it will be the mirror image. So this the both of the mirror image, they are not super in each other. Okay, they are not super possible in each other. For this reason, it will be optically active. So this isomers, it will be optically active. So if I give you the three-dimensional figure for this molecule, this is the three-dimensional figure. Look, this cycle it will be on the plane, this cycle on the plane, and this cycle it will be through the plane. That means this near from you and this far from you. So this molecules that has no plane of symmetry, okay, no plane of symmetry. But if we replace here, for example, we have NO2 with NO2, so it will be optically inactive. But this group, not like this group, it will be optically active. Okay, so the condition here must be the groups they are substituted on the cycle must be different group, not the same group. So again, look to this from another side. If you look, this cycle, it is not with the same plane of this cycle. Okay, not the same of this cycle. So this type of the stereoisomers, due to there are no free rotation between the two cycles. Okay, that meaning this cycle cannot be rotate. So what is the condition here to be the molecules like this type to be optically active? So we have three requirements. That meaning three conditions to be optically active. And what in each type of compound? And biphenyl compounds. Okay. So must be restricted rotation. There is no free rotation between the two cycles. So also each individual ring must be unsymmetrical. Okay, each individual ring must be unsymmetrical. I said to you before that if one ring has two identical groups, the molecule will be optically inactive. That meaning that two substituted group on the cycle must be different group. طبعا if two group they are different, already it will be there are non plane of symmetry. We say non-planarity. The rings must be stay out of the plane with each other, and there is no plane of symmetry. Look, this group CO2H and this NO2, this CO2H, this CO2, but we have here the chlor. Also, this it will be optically active because there is no plane of symmetry. Also, we have here NO2, here hydrogen, different group. Here NO2, here CO2, different group. That meaning it will be optically active. For example, for this type of isomers, is the vancomycin, is the drug compound. So if you look to here, where's the biphenyl compound? Here it is the biphenyl compound, this cycle and this cycle, and this is optically active due to there is no rotation between these two cycle and this two cycle here, this and this. So also we have another example is the BINAP, is the famous catalyst used in the lab to create other chemical molecules. Also look, this cycle and this cycle here, they are not on the same plane, the three-dimensional here. Look, this for example on the plane, this through the plane, both of this two cycle and this two cycle not on the same plane. Also this it will be optically active. We stopped this lecture to be finished. The first lecture will be finished to here,
and inshallah the second lecture we start with the fused ring benzenoid compound. Thank you for listening and see you later.